Hello everyone, welcome to the final lecture of week 8. So this week had been a bit heavy in the technical side, and this lecture would be one of the last component on how do you align to user preferences, and this will also be a bit heavy. Okay, so what we will do in this lecture, we will understand direct preference optimization as another way of aligning to user preferences. So these will be the concepts that we'll cover. So what is the objective of DPO? Now after doing that, we will just quickly see what are the advantage of DPO versus PPO that we saw in the last lecture. And then finally, we will end up seeing a very simple way technique by which you can do alignment to user preferences. And this is back of an BON sampling. Okay. So that's what we will cover in this particular lecture. So now what is direct preference optimization? So now you would recall RLHF pipeline, right, by now. So what do you do? So you have a language model that you want to train through RL. Yes. So this policy, LM policy, you want to train through RL. Now what is the idea? You keep on giving a prompt, you generate a completion. Now when you generate a completion, so you have a completion. Now you don't have a human in the loop to give it a reward, so you make use of a reward model that given any completion will give a reward, that how good or bad that is. And this reward is used by various ways. You saw a simple way and then also a complicated way of doing that to train my LM policy, right? And reward model is already frozen. Now how do you train reward model? For training reward model, you need some preference data, that there is a prompt, there is a winning sample and there is a losing sample. And I say, okay, my reward model should start giving a higher reward to the winning sample than the losing sample, and by that I learn, given any prompt, any completion, how to give a reward, right? So that's the idea. So you first train a reward model, then an RN model. Now DPO asks this question: do we really need these two phases, or can we directly use the preference data to learn the final language model without going through the RL phase? So that's what is DPO. So you have a prompt. You have a preference data that for this prompt, this particular completion is better than another completion. You have winning and losing sample, and you use that directly to tune your final language model, right? And that is DPO. So it looks much simpler than this RLHF phase, but how do you go from RLHF to DPO and still get the same advantage? Like, are they very similar? Are these objectives very similar? And that's what we will see in this lecture, right? So, and the reason is that it's not easy task to train this reward model, and if the reward model is not good, I mean that will affect the whole policy training, because that is entirely dependent on your reward model, right? Because in policy training you explore through new prompts, new generation, and unless you have a good reward model, you will not know whether these are good generations or not. So here you rely on directly human data. So you have a prompt and human labeled preference data that this completion is better than another, and then you directly use that to train your LM, right? So that's the difference. So DPO, as we are seeing, can simplify this entire training framework by eliminating the need for explicitly model rewards. And how it does that? It directly optimizes the policy based on user preferences, rather than having a separate reward model. So you don't have a separate reward model in case of DPO, right? That you get rid of that. Okay. This is another visualization for the same the PPO versus DPO RLHF PPO perspective, where you still use the preference data. You see the starting point is similar for both PPO and DPO. You need the preference data, but in RLHF or PPO, what you do, you train a reward model, right, first of all, and then you don't need this preference data, right? Then you don't make use of preference data in the RLHF phase. What you do, you use the reward model. So you give your agent in the wild, you give prompt, and you learn the policy and the value function, right? And you have the new model. So you don't use the preference data anymore. While in DPO, what you will do, you will directly use the preference data to train your policy, right? So you don't have a reward model separately. Okay, so this becomes much more directly used in DPO, right? And the policy is trained on this data without the need for reward model training. Okay, and why are these two equivalent is what we will see. So we will see they are equivalent. Okay. So let's see, how do you form the DPO objective? How do you go from RLHF to DPO? So let's recap, the RLHF objective. The simpler one, so where what we said, so this is in terms of minimization. So we have, so the loss function is the quality of the output y. So you have the reward that you have got. So x is your input and y is your completion, and RXY is your reward model. You want a high reward, so negation, and so your actual objective to maximize was RXY, you want to maximize the reward minus the penalty, beta times the penalty between the model and a ref model, right? That was your objective. So now if you want to convert into loss, you do a minus sign, so minus of reward plus beta of this, just negation, and you say you want to minimize this. You want to minimize this loss. So this becomes your loss function, right, entirely. That you want to minimize, right. So that is your simplified RLHF objective. Now here, if you see, reward model is already trained, right? You are not training this anymore, and the ref policy is already trained. This is also frozen. So the only thing that you are training are this pi theta. This is your LM policy. Right. So only this particular term depends on the target policy, and nothing else depends on the target policy. Okay. Now, given that understanding, so we have this particular loss function where only one term depends on the policy and other are frozen, they don't depend on the policy. Now, what we are doing now, we say, okay, let's rearrange this, right? We will not, we will still use the same form, but let's rearrange this such that we take this as an independent term. So let's take it here. So beta log pi theta y over x, y given x, minus beta log pi theta y given x minus RXY. Same thing, just rearranged. Okay. Now I am doing argument of something, and beta is just a constant. So what if I divide every thing by beta? So I get this, and it is also 1 by beta, right? And I put a minus sign here. So now this is one term that is dependent on theta, and I have another term, right? So that I log pi theta y given x plus 1 by beta r x y. You can put log common and you get exp here, right? So this is nothing but plus log of exp something. So you take log of log a plus log b is log of ab, right? So use that idea. So you get log of pi theta ref y over x, y given x, an exponent of 1 by beta r by r x y, right? I hope that is clear. So now you get two terms exactly. One is dependent on the policy parameters theta, another one is not dependent on parameters theta. Okay, we are still minimizing the same thing, and they are equivalent, right? They are equivalent. Okay. Now given this, now what we will do, so if you look closely, what is this equation doing? So this objective function is a difference between the log probability distribution of y, right, given x, conditional distribution of y given x, and another function of y, right, log of another function of y. So actually, yeah, yep. So they are difference of two functions. One is log of a distribution, another is log of some function of y. Now, typically when we have objective functions, we typically say, okay, we have a probability distribution, log of probability distribution minus log of another probability distribution. So this is not an ideal form. So we want to still stick with that, retain it, but can we rearrange it again somehow so that it becomes a difference of two probability distributions, right? So because you prefer to say difference of two distributions, right? So because once we have difference of two distributions, this can be divergence, seen as a divergence, right, of distributions. So how do I convert the second term into a log probability distribution over y, Right? So, this one I want to convert into a log of some probability distribution. Now, how do we do that? So, let us see this. So, the simple idea is let us see the second term as a log of some unnormalized probability distribution, okay, because pi theta times exponent this, let us say this is the unnormalized probability distribution. Once you normalize, this becomes a probability distribution. Okay. So, now okay, if this is unnormalized, right, if this is unnormalized, how do you normalize this? Okay, you say okay, over all y you compute this. So, this is a normalization factor. So, say okay, I will pi theta ref y given x exp 1 by beta r x y, and I will do it over all y, and this becomes a normalization. This becomes a normalization. Okay, very good. So, that means if I want to convert into a normalized distribution, I will divide log this quantity divide by gx, right. So, I will come here. So, this is my normalized distribution pi star y given x. So, then I can say log pi theta y given x minus log pi star y given x, right. Okay. So, what do I need to do so that I can write this expression as this by gx? It is very easy. I mean, you divide by gx and you multiply by gx. So, you can say okay, I'll multiply by a gx term and divide by gx term, and this gx terms I will take inside, and this will become a probability distribution, and I will have another gx, right. So, minus log pi star y given x, and because it is multiplication minus minus log gx, right. That is what I will get. So, that is what I do. So, I rewrite this using gx. So, I say okay, this was my quantity, I divide by gx and multiply by gx, right, and we saw this will give you minus log gx and this gives you this, and this we know what is that. So, this is exactly our pi star y given x, right. So, we got what we wanted. We have now a difference into log distributions, log pi theta y given x minus log pi star y given x, but we have an extra this minus log gx term. Okay, let us bear with this, and we will see that this will actually vanish later on. So, right, and okay, so now I will take these two terms together because I want to call them KL divergence between the pi theta and pi star, and I have minus expectation over log gx, right. So, these are two terms I get. One is a KL divergence, another one that is normalization factor, and this is constant with respect to theta, right, because we saw this is gx is coming from theta ref, there is no theta term, it is constant with respect to the theta parameter. So, this is how I can write the objective. Okay. Good. So, now what is the value of so let us continue. So, we have this objective function, right. Now, because this is constant with respect to theta, when I am doing argmin theta, right, which this will not matter, right, this will not change anything. So, that means what I will do, I will say my theta hat, the optimal parameters are those that minimize the scale divergence, right, because this has no dependence on theta. Okay. Now, what is the distribution pi star that will minimize this, right? I mean, what is that pi theta y given x that will minimize this whole quantity? You know, this divergence will be 0 when they are the same distributions. So, divergence is 0 when they are the same distributions. So, what does that mean? If I say pi theta y given x is pi star y given x, let us now put back pi star y given x, that was nothing but this quantity, right, pi theta ref y given x exp 1 by beta r x y divided by gx. So, gx is not gone, right, this is very important, gx is still there, but let us see. So, what will this give me, right, what will this give me? This is saying okay, what should be pi theta y given x in terms of pi ref y given x and something a form of r x y and gx, right. So, this is the solution to this optimization problem, but where is my DPO objective? Now, what do we get from here is something interesting. We say okay, now given this form, let us see what is my reward model, right. So, this is my optimal value, right. So, what is the corresponding reward? I can find the corresponding reward in terms of pi theta and pi theta ref. That is what I get. So, I say okay, this is my this is what I want to achieve, pi theta y given x should be this. Now, can we express the reward r x y as? So, now you put these things, I mean you will say okay, pi theta y given x divide by pi theta ref y given x, there is an exponent, so there will be a log, and you put g x there, so plus log g x, and there is a beta term. So, if you rearrange, you will say 1 by beta r x y, right, e x p is pi theta y given x upon pi theta ref y given x, right, times g x. So, if you remove exponent, you will say is equal to log of this plus log of this, right, and then you want to remove beta, you say okay, beta times this, and you get this form, right. Now, this is what is very interesting. So, we are saying by solving that objective, we got a reward model, right. So, this is our reward model. So, this is a reward model, analytic form of reward model in terms of my policy parameters and the ref model, right, from which I am starting, plus some normalization that we still want to get rid of, right. I do not know how to compute it. So, I want to still get rid of this, we will see how. Now, this is my reward model. So, then what should I do? I say okay, I have my reward model in terms of my model parameters. So, I can use that to train my model parameters. Now, take your data, train my reward model, and through the training you train your pi theta. That is the idea. So, this is the analytic form. Now, by training your reward model is equivalent to train your pi theta, and that is the very interesting idea. So, how do I train my reward model? No, okay, I know this. So, we can go back to the Bradley-Terry model, right. So, that is all. So, we have this form of reward model. Now, we use Bradley-Terry model to train this reward model, then that actually will train my pi theta, right, because reward model is written in terms of this. So, what is done? So, this is your reward model, right. Now, what is the Bradley-Terry model? Say okay, probability that y a is the winning sample from the preference data, y b is the losing sample, given x as the input. The probability is sigmoid of r x y a winning sample minus reward for the losing sample. Okay, I will put back the analytical form. So, I will say okay, this is beta times log pi theta y a given x divided pi theta ref y a given x plus log g x minus, and you see how g x will vanish. So, you see okay, g x will cancel out, good. I did not know how to compute it. So, it is gone. So, now it is sigmoid of beta log pi theta by pi theta ref for the winning sample minus beta log pi theta over pi theta ref for the losing sample, right. Okay. So, that is a very good form. So, now I only have my LM model and the reference model and the winning sample and losing sample. Okay. So, it converts the difference in rewards into the difference in ratio form functions, right, and we have seen ratio functions even in PPO. So, and we do not need to compute the value of g x, the most important thing. So, how do we train my policy? We will say okay, the loss will become minus expected value for log p r theta y a winning sample, y b losing sample, like minus log probability of this. So, minus log of this sigmoid. So, yeah, so the loss function depends on the parameters of the policy, right, rather than the parameters of the reward model. Good. So, now what does this loss function look like? I mean, does that make sense intuitively if you see the form? So, what it is actually trying to do, right? So, we know that you will, what do you really want to do with this loss function? You want this to be a large quantity, right? This should be a large quantity, otherwise you will train. So, when will this be a large quantity? When this term is positive and this term is negative, because there is negation sign. So, negation of negative will become positive. So, I want this term to be positive, this term to be negative, ideal case, right. What does that mean, this to be positive? That means log of, or which means pi theta of y a given x should be greater than pi theta. Let me write this, pi theta y winning sample given x, this is pi theta, y winning sample given x should be higher than pi theta ref y winning given x. What does that mean? Say theta ref is our base model, right, and you have a winning sample given a prompt. So, given a prompt, the ref model will give some probability the winning completion anyway, right. What you are saying, my theta model, the policy model should give it even a higher probability than what the base model was giving. That makes sense. So, this is my user preference. I want to go towards that, right, towards the winning sample. So, I should start giving it a higher probability than the base model was giving, and that is a very interesting idea. Okay. So, I want to do that. Good. What is the second term? So, it is saying okay, pi theta y losing sample given x should be less than pi theta ref y losing sample given x. What does it mean? So, my reference model was giving some probability to the losing sample. My LM model, the RL whatever you want to call it, the policy model should give it even a smaller probability than that, right. So, it should decrease the probability for the losing sample and increase the probability for the winning sample. That is what this function is doing, and if it is not happening, you will update your policy, right, so that it happens. So, because if it is not, if it is the reverse direction, that it is giving a higher probability losing sample than the ref model and a lower probability of the winning sample than the ref model, then this will be a negative term, and sigmoid of negative will be close to right, close to 0. No, sorry, first of all, log of, yeah, it will be a negative term, highly negative term, it will be close to 0, right, and right. So, what will happen here, if this is positive, highly positive, and this is highly negative, this quantity is positive, right, this log of higher than 1 is positive, log of less than 1 is negative, right. So, high positive value, yeah, a sigmoid of a high positive value will be close to 1, and then you have a log here, right? That is what I was missing. So, sigmoid of this will be a value between 0 and 1. So, if it is a highly positive, it will be here. If it is highly negative, this is desired case, and this is not desired case. So, in the desired case, what will happen? It is close to 1, and then I am putting a log close to 1. So, that will be close to 0, and this is a close to 0 and put a log, it will become very high negative value, and with a negative sign you have a very high loss, right. So, yeah, that is how you train this model. Okay. Now, in the literature there are many variants have come after DPO. So, one is KTO, for example, proposed in this paper. So, what they say, okay, for training DPO you need a preference data, that means you need prompt, a winning sample and a losing sample, and you need a lot of such pairs, right, lot of such tuples you can say. Now, what if you only have a prompt and just know given a completion, is the user preferring it or not preferring it. So, you do not have a pair, but you just have individual things, that given a prompt and a completion, is it preferred or not. They said okay, they just made a modification where they are saying okay, if it is desirable you have this function, if it is not desirable just the reverse of this, I mean negation of this in the sigmoid. So, they will have opposite behaviors, and then you have a final objective, right. So, KTO is a variation of DPO where they try to work with even when you have a single labeling at a single utterance level, that is preferred or not preferred, right. So, that is what is KTO, and there are other variants like SIMPO and so on, CTO, ITO, there are many variants that are available. But idea is similar, that you can use directly the user preference data, right, either the pairs, that this is a winning or losing sample, or the individual data, that this is preferred, this is not preferred, but may not be put together. Now these ideas are very important because you can now directly fine tune models based on these ideas, right. So you can say, okay, I have a model that does something, now you want to make it more aligned to your preferences. So you say you want to make it more formal or whatever, right. So you need a lot of data where you say, okay, this is a preferred thing, this is not preferred thing. And then you train the model so that it takes you to the preferred thing and away from the not preferred thing, right. So you start from a base model, the ref model, and using the user preference data, you take it to pi theta that aligns to user preference, because the objective is it will start giving a higher probability to the preferred things than what the ref model is doing. You start giving a low probability to the not so preferred thing than what the ref model is doing. Okay. Now the advantage of DPO, the main is simplicity and efficiency, as you can see. So it's very straightforward because you directly optimize for the preference based feedback, right. You don't rely on the reward model separately. Reward is coming out analytically here, and it's more sample efficient because you already have a fixed data, right, on which you are training the model. While you in PPO you have to do it at runtime. You explore by generating some completion and putting a reward model. So you have a fixed data set here, and that's why it has become a very popular method for human preference alignment. So especially when you think RL is challenging for you, you can directly go for DPO model, but you need a preference data. So completion and preference data, and people also see it as an offline RL method. Now what about PPO? I mean, should we go for PPO? So PPO itself, which is an online RL method, which has its own advantage, like because you explore new states through interaction. Because what is happening in DPO is completely limited by the preference data that you have. But you are not allowed as such to explore new states, right. So that's the benefit of online RL, that it will allow agent to continuously adapt to changes in environment. So because you learn from real time feedback, so they are not constrained by the static pre-collected data, because you had doing new generation and getting a reward on that, and that's how you are training it. You can discover new strategies. So this is what is important, that you can do exploration that is not allowed, I mean not possible in the previous the DPO kind of scenario. So you can cover a wide range of pairs and you can improve generalization. So it's a very critical aspect, right. So applying these large language models. Okay. Now finally I'll end this lecture by giving a slight idea that, oh, what if see, so we talked about RLHF, we talked about PPO variation of that, we talked about DPO, right. All of these are there, but there is one thing in common. You have to have some preference data, then you either train a reward model, then do RL, or directly fine tune it, right, using this DPO objective. So you need to still fine tune them, right. So and this can be very computationally expensive, right, and you have a huge cost in doing this stuff. This is not a simple like few shot training and all. It's actually fine tuning an RL. So what is an alternative? So suppose I have a reward model, a simple reward model that I have not trained, but I know. Say it can be somebody else has trained it. I directly want to use that, or you can say it's a very simple reward model that can give some scores, right. Maybe I have a verifier that can say this is good, this is not good, right. Simple verifier. So I have a reward model, but I don't want to train an RL policy, right. Say I want to avoid training RL policy. What can I do? So can I do something at the inference time? Can I do something at the training time that is easier than what I have talked about? So there are things that you can still do. So let's say you have a reward model and assume this is like given a prompt and a completion will give you a reward, right. That's what is the idea. It can be a simple verifier that you can easily write a program for, or some reward model that you know, right. So what can you do? So the simplest thing you can do at inference time is, we call it BON sampling or best of n sampling. What is the idea? So fine. So you have the input sequence X, right, and you want to generate a completion for that. So rather than generating one completion, you generate n alternative completions, right. So don't generate the same completion multiple times, it will not help. But see, how would you generate multiple completions? You can vary, for example, the sampling method. If you're using random sampling, you can vary the temperature. So and actually random sampling with the same temperature also you will get different explorations if your temperature is set like somewhere where it can explore, right. So So what you will do, you will have some way in which you can generate n alternative outputs from an input. These are your n outputs. Now you have a reward model, you find out which one is the best among these, right? And you can select the best one. This is just an inference time used, right? So you can have a reward model, find out among all completions which one is the best. No RL or training involved. Now, can I also use that to train language models? So we say, okay, why can't I use that for training also? So I say, okay, I have my reward model. Now I'll do the same thing. I'll give a prompt, let it generate n completions. I use my reward model to find out the best output from these n list. And I'll say this is my preferred response, and anything else can be my not preferred response or whatever. So I can use that to induce human preference into training by use of this reward model. And this is also known as the rejection sampling method in the literature. Okay. So yeah, I mean, we talked about a very simple method, Boolean sampling, and you can also use that in training time, because you can select which output is the best among some n possibilities. Okay. So okay, for this lecture, foundations of large language models would be a good reference. You can go through that. This is available on archive, and that also completes our week 8, which was a bit heavy in technique wise. In the next week, we will start with the prompting. That will be slightly easier than what we are doing right now. Okay, then thank you.